By the end of this video, you will be able to analyze simple systems for energy storage by drawing system schema and qualitative pie charts. Before we go into the lesson, why don't we show you what it's going to look like when you are able to do the objective. Alright, we're going to take a look at this jump here and identify some moments about when he's about to jump, about midair, landing and rolling. It's kind of slowing down as he's doing that. So there's 4 events with the person interacting with the ground and that cliff and the earth field. That's our system. Everything's inside. So we have, looks like he's not really changing height as he jumps across. So this potential energy due to gravity is about the same, but he is speeding up. So I'm going to show his kinetic energy gaining as he jumps. Because he pushes off, that probably used some chemical potential energy. As he lands, his potential energy due to gravity is used up and he's going faster, so kinetic energy with a little slice of internal energy. As he lands and dissipates some of that energy, he starts to slow down. Wow, that was a lot of information all really fast. Let's see step by step how that works. So there's a question. What do you know about energy? Basically tell me, what is energy? When doing energy analysis, we have to ask some questions. To be effective at analyzing energy in situations, we have to know how to answer these 3 questions. What is the system? Where does the energy come from? And where does it go? We'll explore some situations, and hopefully you'll see some familiar ones. One of the stations that you worked with during your lab was the Astro Blaster, which involved a large ball and a small ball. Let's see what goes on. Whoa, what happened there? How do we know that energy was involved? Energy doesn't always involve motion. We can also find changes in other properties of the system. For example, boiling a pot of water on your stove to make some tea. When you first start heating the water, you don't really notice any movement in the water like you see here. But you do know that the temperature is increasing, a fact that we can observe by throwing a thermometer into the water and watching the thermometer show us the temperature increasing, which indicates that there is something else going on. We don't really see the water move until we reach that boiling point. So we know that we're adding energy to the pot of water. So when we're investigating energy in a system, we're not just looking for motion. What would be the overall thing that we're looking for? We would be looking for changes. If there are changes in something we are observing, we know there is energy involved. Energy is a measure of the capability to produce change. Now that we have a definition for energy, we need to focus our analysis. Basically set boundaries on what we care about. This is called defining a system of interest. Let's think about what this means. Let's look at the Astro Blaster again. What are we looking at? What is changing? List all the objects that may have something to do with the energy involved. Well, how is it that objects fall in the first place? Well, that's due to an interaction with Earth's gravitational field. Guess what? We get to include the Earth field as an object in our system. So, my question is, do we care about anything else in the video? Do we care about the wall in the background? The hat? The sun? No. These objects are ignored because they do not have any effect on the major changes we witness. Basically, we are carving out a little section of the universe for us to focus on for our analysis. So now I have a definition for you. A system is a portion of the universe that has been chosen for studying the changes that take place within it in response to varying conditions. Everything that can directly affect the system but is not in the system is called the surroundings. Part of defining the system is also defining the moments we care about within the system. You can think of energy analysis like telling a story. For every change, there is at least a beginning and an end. We call these moments events or states. So we have another definition. The definition of an event or state is a particular configuration of the system and its surroundings at a particular moment in time. Here is a moment in time for the Astro Blaster. This is the moment just before I drop those objects. We have several moments we can look at. Here are the ones I chose. We have the ball being dropped, the ball just about to hit the ground, the little ball launching off the big ball, and that big ball is bouncing up. In fact, in this picture, it's bounced as high as it will go. And lastly, the little ball at the very top of its arc, which is out of the picture here, but using the shadow, it's just above the frame. Cool. So, a technique to identify the system is a diagrammatic tool called the system schema. In the system schema, you get to represent each object in the situation you are viewing with a labeled oval or circle. The next step is to indicate interactions between objects with a double-headed arrow. Then identify the system by encircling the objects with a dashed line. Well, how do you recognize an interaction in the first place? Most interactions occur when there's obvious contact between them. However, things like magnets and the Earth can interact with objects they are not touching through their fields. These interactions involve energy stored in magnetic or gravitational fields between the magnet or Earth and some other object. Alright, so let's try it out. Let's go ahead and draw the system schema for the situation. So we have a big ball, a little ball, we have the person, we have the ground, and we have the Earth field. We now make the interactions with double-headed arrows indicating the influence of each object on each other through contact or through a field. Then we decide that everything is going to be inside the system by putting a dashed line all the way around it. Note that you don't always have to include everything in the system. We could leave the person out, for example. We could also just circle the big ball and the little ball. Or we could even just leave everything out except for the big ball. It kind of depends on what you're trying to go for. Now, why don't you give it a shot? In this sequence, I jump from steps to the ground and roll. Here it is again in slow motion. Launching off the steps into the air, hitting the ground, and rolling, and getting up, and moving forward still. So now I want you to draw the system schema. Here's what I came up with. How does that compare to yours? The ways we work with energy are similar to the ways we work with money. So let's go ahead and make a comparison of the two. So let's get two columns going, one with energy and one with money. The symbol for energy is capital E, and the symbol for money is, of course, the dollar sign. Well, in the United States anyway. So let's think about the ways we work with energy. The first way is storage. Energy storage is usually called potential energy. When we're storing money, we're usually thinking about a savings account. When we're using that money to do things that are very noticeable, like motion in case of energy, that would be called kinetic energy. And that money that is easily movable and usable is usually stuck in a checking account. The next thing we look at is something we call internal. Remember, we made that system. Everything that's inside the system, all those interactions inside the system can store energy. So if we add up all those, we get the total amount of energy inside the system. If you were thinking about your savings account and checking account, it's all your accounts at the bank. If we have interactions that are crossing the boundary of our system, that means an object from the outside of the system is interacting with the inside of the system, or vice versa. Well, that's what we call external, which means we're going to have energy transferred out or in to the system. This would be like if you were to make money from another account or spend money from your account. So these are accounts that aren't yours. And finally, we like to consider energy that is lost. But really it isn't lost, it's still inside the system, it's just not recoverable. And we sometimes make transactions that require a fee. So that's where that money goes. We can never recover it because the bank has it now. In this class, we'll represent energy that's internal to a system with the symbol E. A subscript on this variable will tell us what type of storage we are dealing with. Here are the most common energy storage modes we will be dealing with. E sub k, that's kinetic energy. E sub g, that's gravitational potential energy. E sub el, that's elastic potential energy. E sub ch, that's chemical potential energy. And finally, E sub int, which is the unrecoverable internal energy still inside the system. Kinetic energy is the energy associated with motion. It's the only energy that can be stored into one object. Gravitational potential energy is the energy associated with an object's interaction with the Earth's gravitational field. You have to include both objects because the interaction between them is where the actual energy is stored. Elastic potential energy is the energy associated with springs or stretchy materials, basically anything that can change its shape and go back on its own. This is another energy that can be stored in the object by itself. We can also think of the energy being stored in the interaction between an object and some other stretchy object. Chemical potential energy is the energy associated with the breaking of molecular bonds or the attaching of molecular bonds. So you'll see great examples of that all the time. Car engines, person moving something, and so on. It is stored in an interaction between the object that has fuel and the thing that it is interacting with. Unrecoverable internal energy is the energy associated with the kinetic energy of the molecules. We don't want to talk about kinetic energy in terms of something that we can just get back, because as soon as it's stored in unrecoverable internal energy, it is quote-unquote lost. We cannot change it back into any of the other modes. So this would be like air resistance, friction, and the random motion of molecules. Again, this is stored either within an object, but can only be stored when there's an interaction between two objects. So how can we represent these storage modes and show that they will transfer back and forth within storage modes but never actually leave the system? Let's identify the system here. We have a skater on the ground who's actually going to be on a track, and the earth is pulling on the skater and the skater's pulling on the earth, so there's an interaction there too. Watch what happens since I'm not part of the system. Watch what happens to the amount of energy stored in the system. Whoa, did you see that? What's that circle represent above the girl's head? We can look at the key and recognize that it says potential. What it really means is that's potential energy due to gravity, or gravitational potential energy. Notice that the size of the pie chart increases as we lift her up. The pie chart doesn't stay the same size because I'm not inside the system. I'm lifting her up from outside the system. For now, we're going to assume everything's inside the system. As soon as I let go, she has all the energy that she's going to get. Watch how the size of the pie chart never changes. But you see that a wedge gets bigger and then smaller, or vice versa. The green wedge gets smaller as she goes up higher, and the blue wedge gets bigger as she goes up higher. And when she goes lower, the blue wedge goes down to 0, and the green wedge is 100%. Notice that the green wedge is the kinetic energy associated with the system. What do you notice about the size of the pie chart? Yeah, it doesn't change. That means the total energy inside the system doesn't change. If there are no interactions crossing the boundary of our system, the energy cannot change. This is called the conservation of energy. Watch what happens when we start to include friction. And when I release her this time, we'll notice something else is going on. This is more realistic. We see some red energy that is there. This is that unrecoverable internal energy. They've labeled it here thermal, but I don't want you to think that it always relates to heat. So when you are working on systems, you have to identify different moments in time. The moment we let go, she has 100% gravitational potential energy. And as we let her go down, we can see that about halfway down, she's got about half of gravitational energy and about half kinetic energy. Because we have some friction involved, we have a tiny wedge of internal energy. As she gets to the bottom, we can see all of the gravitational energy is gone.
and is stored as kinetic energy, we do have a larger wedge of unrecoverable internal energy. As she goes up the ramp, we'll stop her at the very top when it's 100% blue. And there's another moment we could focus on. She's lost a quarter of the energy by now, and so that she will not go as fast at the bottom of the next turn. So we can see it's all stored as gravitational potential energy, and a little bit is stored as unrecoverable internal energy. So when you are drawing your pie charts, make all the circles the same size. Then cut out little wedges that represent how much you think the energy is there. We'll get better at this as we practice more.
Now let's put it all together. Here's my jump again. I'm going to pick out 5 moments for you, and you are going to draw the pie charts. Let's see what you guys come up with. Remember the 3 questions. What is the system? Where does the energy come from? And where does it go? All right, here are the 5 moments. Just about to jump. At the highest point I jump. Right before I land. In the process of landing. And finally, getting up and moving to the right. Try it out. See what you come up with.